Quantum scattering from a spherical shell. How does a delta function shape the future of a particle's path? Let's break it down. What you'll need to know for this potential and this problem in general is that when we are trying to localize a potential, here in the very inner, where V is not equal to 0, we have what's called the scattering region. So no approximations can be applied, and we have the radial wave equation. Outside of that, we have what's called the intermediate region. And this is where we can approximate the potential to 0 on its effect, and we only need the centrifugal term, this thing here. And then outside, where Kr is much greater than 1, we have the radiation zone. And this matches with what we saw back in Griffith's electrodynamics book, so this is pretty cool. All of this together is what we call the partial wave analysis, and this slide came from Dr. Sergey, clearly from spring 2001, so go check out his stuff. But with this, let's jump into the question. Alright, so this is problem 10.4 out of Griffith's Intro to Quantum Mechanics, 3rd edition, of course. And what it's asking us to do is consider the case of low energy scattering from a spherical delta function shell, where we have V of r is equal to some constant alpha with the delta potential located at A, where alpha and A are constants. Calculate the scattering amplitude, that is f of theta, the differential cross-section, d of theta, which we saw this was a big thing to find in the Rutherford scattering, and the total cross-section sigma. Assume here that Ka is much less than 1. Okay, so that should tell you a lot about what regions we're in. Okay, that should tell you that we're in the scattering and intermediate regions. So that only the L equals 0 terms contribute significantly. This is big for us, so we want to keep that in mind. The main problem, of course, is to determine C0, which is the partial wave amplitudes. And express your answer in terms of the dimensionless quantities beta is equal to this constant. So, here we have, why do we care? Well, this is all due to partial wave analysis, and it's a technique that breaks down a scattering problem into angular momentum components known as partial waves. Very nice for us, and one of the big approximation methods covered in this chapter. But, of course, as an approximation method, I'm curious, where does this method break down? That being said, this problem has a lot of moving parts in it, so please be aware that the PDF is still available for you to follow along, or if you just want it, just comment and I'll send you the link. There's a lot of the algebra that's left out of here, otherwise you would spend half the video on just the algebra, but rest assured it is in the PDF, so with that, let's dive into this question and see what we need to do. Alright, so for this, we have stop number 1, and in order to solve this, we are told that we only need the L equals 0 terms. So, the exterior region we can find from equation 10.29. Exterior meaning that R is greater than A, wherever the potential is localized to. So since we're summing to 0, all we have is one term. So if we plug in zeros everywhere, where you can see in the red, we had 1 to the 0, or I to the 0 gives us 1, 2 times 0 gives us 0, so then we end up with a plus 1 here, no big deal. We have J0, H0 with the 1 up here, and P0, and what these represent is, here the J0 is the spherical Bessel function, and in the PDF I include a link to the resource where you can look up these tables. Here's what we call the spherical Hankel function of the first kind, and that's indicated with the 1 up top, 0th order of course, and that's found in table 10.1. And of course our old friend P of 0, so 0th order, is the Legendre polynomials, and that was found in table 4.1. Thankfully, since we only need the 0th order, we just get a sine Kr over Kr, then we get a negative I e to the IKr over Kr, and the Legendre is just 1 there, so we're good to go. Again, here A follows down, 1 it's transferred down because of the 0, and we see we get some algebra to clean up, cancel the k's, things like that. The 1 and 1, they go to, or the I and I go to negative I squared, which is negative 1, so double negative gives us a positive, and we see what the solution should look like outside of A. Now we have to determine what the solution on the inside of A would look like. And to do this, for the internal region, we need equation 10.18. And here is the linear combination of the spherical Hankel functions, and we can go ahead and plug them in. This is not, again, a well-known script. A lot of other tables use a different notation, but this, again, is in that link to the tables that we have, and you just have to pick out the right one. So from this, we see that we have sine of Kr for the spherical Bessel, excuse me. This is the spherical Bessel as well. That's in the table. But we see that applying these definitions for the 0th order here, B has to be canceled because remember, the limit of sine of x over x went to 1. The limit of cosine x over x, that blows up there. So we can't have this as a solution, otherwise we blow up at the origin. And this boundary condition here itself applies regardless of which case of L you have. And if you need more proof of that, then go ahead and check the orthogonality of the Legendre polynomials. Nevertheless, though, we see what we have here, and we're good to go. This simplifies down thanks to getting rid of that big B, and we see what the solution to the inside region should be. And that gives us the function that we need in a piecewise definition, which then leads us straight to stop number 2, which is applying the boundary conditions. Because we have two equations, we have a constant big A and a constant little b that need to be solved. The only way to solve them is with boundary conditions. But the thing with the boundary conditions is that we need the function to be continuous at the boundary. That makes sense. So we just set the two equal to each other at A, which you can see with the color coded. But because this is a delta function, and we saw this happen in chapter 2, I believe, with some of the potentials that we had, both the delta function potential and a finite square well, we have to take into account that the derivative is discontinuous at the boundary. And if you remember, that meant that we had to take a derivative on one side minus the derivative on the other side, and it turned into a big heaping mess of algebra. So keep that in mind when we apply this. The reason why we need to apply another boundary condition is because we have two unknowns, and we can't solve that with one equation. We need another one. So let's get to solving this other boundary condition and tidy away. So after that, what we notice here is that because we have inside the region, we have the full solution that we need for the radial wave equation, and so we have to integrate out the radial wave equation first. Of course, we have the Schrodinger equation modified for the radial coordinates and the energy over here. But again, we made a substitution to get rid of the r's and the placement of u's. But regardless of that, what we see here is that we have a 0, 0 for the L terms. So when we have a 0 up in the numerator, that gives the whole fraction as a 0 times these constant, that goes to 0. So we're good just to get rid of that term as a whole. Now we see we split this up, and we're good to go pretty much to split up all the terms. The delta function, you have to use the shifting property. That gives us u at A with alpha out front. This right here gives us the delta u prime because we integrate out one derivative. And again, we have to go to the delta because we're looking at both sides. And looking at both sides, we see that the E should be the same because the energy needs to be the energy. So we get a 0 over here due to the delta fact. And if we solve this for delta u prime, we get this equation, which is very reminiscent of what we saw in chapter 2. So definitely be aware of that, and that's what we're going to use. But now remember, when we did the substitution originally for the wave equation back in chapter 4, right, when we not translated, but converted it to spherical coordinates, we let u equal little r big R. And if we take the derivative, we see we have a product rule here. So we get little r goes to 1, big R stays untouched. Then we leave little r alone, go to big R prime. So that's just the product rule, easy peasy. But when we take the difference here, we see that big R is supposed to be the same, so that goes to 0. And we are left with A because now we're applying it at the boundary. And then delta R prime, we don't know what its derivative is. And we're assuming this is the function. So we're going to have to modify this once again, put in all our substitutions, and we're good to go. Now here we have delta u prime equals all this, and we're going to convert this into the function that we found in the first stop, and then we'll go ahead and see how the boundary condition applies itself to that case. But before we do that, if you're finding this helpful, don't forget to give it a thumbs up. It helps more curious minds like you discover this content and definitely helps us grow. So, let's continue. Alright, so now applying to our case, where u gets substituted in for phi prime. Guess I have a typo here. We also substituted out all those constants for the beta that we were told in the opening question. But what this delta prime, delta phi prime, or psi prime represents is I need the derivative on the outside minus the derivative on the inside. So we're going to have a lot to do, and then evaluate it at the boundary. And this is where the PDF has all of the nitty-gritty details on this, but it's really not bad. It just takes a lot of steps to simplify all the algebra. And then, of course, we need to set this equal to the function at the boundary. And this gives us a great leniency here because we can choose which side we want to put in. So why not put in the inside where it's an easier function to see? Now, on the other side, the derivative of the r greater than a part of the piecewise function, you just need a quotient rule here, another quotient rule for the exponential. Here, you just need one quotient rule. And then once we go ahead and divide up these fractions, so to speak, we see some cancellations with a here in the denominator, here in the numerator, or none here, cancel, and all that other fun stuff for the algebra. We can group these things in terms of what's divided by Ka. And so whether we need to force the K here, which would what we did for the exponential term here, we just put another square there. We see that after doing that, when we factor out a K squared here, Ka squared here after splitting this up, we see that this cancellation comes courtesy of boundary condition 1 equation, and all these constants, they equal out perfectly. So to me, this was a wonderful way to cancel out and simplify our lives. Now we see that we just have one term with big A up front here. This little b here, this term with the negative, can get pushed to that side, and then we can simplify the rest. So after pushing that b term over and factoring out everything that we can that's common, we get an a over big A over little a, and then we get a little b over little a again, but both a's cancel, so we're good. Now, to eliminate b, we can refer back to boundary condition 1 again. And if we substitute that in, by solving for b, of course, we see that we substitute in a constant a here, and all the functions, and then we had that sine Ka over Ka that we just needed to multiply the reciprocal to both sides for the cancel, and we're good to go. Now, what I want to carefully coordinate with the colors here that I did in the PDF was Ka here gets left-hand distributed, so we're pushing this thing into this bracket, and this sign here gets pushed into this bracket, and we do that for convenience of canceling. This sign here will cancel with that. This sine and cosine combo get here, so we see that that's why we're missing a sign here. This Ka cancels that Ka. This A cancels that A, and that's why we have a K here. And then, of course, we cancel A and A. So with this, we executed our boundary conditions and got rid of the constants big A and little b, and now we're good to go. From here, we go on to stop number 3, where we're looking for the partial wave amplitude, which is this A0. And to do this, we're going to have to take some more algebra and just crank it out. So we have to distribute this, so FOIL this bracket and that bracket out. After doing so, we get some nice cancellations. This sign and that sign cancel. Then you have this sign and this constant. This exponential with this exponential with that, as you see here. And upon doing so, we cancel the cosine and cosine. But after that, we note that we have an A0 Ke, some exponential function here, an A0 Ke here, and an A0 E here, but we can put a K there by multiplying by K over K. So we're going to put these exponentials and the A0s to one side and then factor them out. And that's what we see here. After we factor them out, all of them have a minus sign because you have to minus these over across the other side of the equal signs. They all have a A0. they all have a k and they all have an exponential, and thus we get an I from this one left here. We get the cosine sine here, and we get the beta alpha, or the beta over a, and then we force a k in there. And of course, that's all equal to our lonely sine out Ka over here. So at this point, what we need to do is apply the assumption that we were given in the question statement. And this was that k times a was much less than 1. And what this means for us is that we're allowed to use the small angle approximation for the trig functions. And this complex exponential is a set of trig functions. Remember, cosine theta plus or minus I sine theta. In this case, it would just be plus I sine theta. But for this, we see that the small angle approximation sine of Ka would be approximately Ka. Cosine would go to 1, so this would go to 1 over Ka. And then because we use Euler's identity here, and we get a cosine plus I sine, we get 1 plus IKA. So be on the lookout for that in the next slide, and we'll be good to go. So let's get to that. Okay, so as to stated, we applied the small angle approximation, and we simplified the exponential down to this, the cosine over sine of this, and the sine of this. A whole host of cancellations here on the right hand side, get rid of them. Now we're going to dump this into the bracket, and after doing so and expanding, again, all the Ka's start to cancel, and we can group together things accordingly. We have a 1 over Ka here and a beta over Ka here, so we can factor that 1 over Ka out. That's what we see here. And then we're left with a whole bunch of constants here. So the fact that Ka is much less than 1 means that this thing is going to be pretty much irrelevant. These two constants here are also going to be irrelevant due to the fact that if I'm taking something and I divide by something really small, I get something really big. So I have a small value here, so this whole term is going to be really big. So big, in fact, that it trumps whatever these terms can contribute. So we use this approximation to whittle this bracket down into just keeping one term. And after that, all we do is divide k, or cancel k and k here, and then solve for beta, or excuse me, we set that this was equal to beta. So from here, we can go ahead and solve for the partial wave amplitude, and we're good to go. And so what we see here is that after the application of all the boundary conditions and all the algebra, we obtain the 0th partial wave amplitude, and now this is going to be the gateway into solving for everything else we need. Now that we have this, we're good to go. The scattering amplitude, f theta, in terms of the partial wave amplitudes, which we just solved for the one case of L that we need, is given by equation 10.25. Which, again, if you look at the actual equation in the PDF, it's a lot longer than what this cheap thing is. But since we only need it the case of L equals 0, you plug in one, you only get one term in the series, so this is the one term. Then, of course, you see we get 2 times 0, that gives us 0, so you're multiplying by 1, so we don't really need that. And again, Legendre of the 0th order is 1, so we're pretty much left with the scattering amplitude f theta is equal to the partial wave amplitude, so we're good to go. We see what it is here. And that helps us tremendously because the differential cross-section is just equation 10.14, and all we had to do here was square what the f theta was, and we're good to go. So square it in the magnitude, we get rid of that negative sign, and now you see we're a bracket or parentheses with all terms squared. Pretty darn cool. And this gives us directly the total cross-section from 10.27, which again was sigma equals 4 pi times all these constants with the magnitude of the partial amplitude squared, or in this case, you just have 4 pi times d, the differential. So tag your 4 pi and you're good to go. You just achieved everything we needed to for this. The hardest part in these problems are determining the function, what it should be in the different regions, and then secondly, applying the appropriate boundary conditions. Anytime you're dealing with differential equations, knowing the boundary conditions and knowing how to apply them are going to eat up most of your time. So be aware of that as you move forward. So, Thank you for watching. That was a fun exploration of another big part of the scattering phenomena that we are now going to move into almost exclusively in physics at some other frontiers. But if you can, share this video with a friend who's also curious about science, and let's grow this learning community together. It helps us a bunch, and all the supporters that have already rang in, all our Patreons, all the people who have supported on Buy Me a Coffee to help the book fund. Thank you, thank you, thank you. If you like what we're doing here, if you like the channel growing, the page growing, please consider supporting and joining the Patreon team or donating if it's within your means. Please don't go outside of that. It's been a hard year for everybody from what I've gathered. So, but you know, science will always be there for us. Learning will always be necessary. So, learning how to learn, understanding problem solving and analytic things, very important to us. And I think that, especially for students, there's a lot of resource out there. So, getting more perspectives on different problems is definitely helpful, especially if you're caught up with one or two steps that makes life annoying. You know, please feel free to give any questions or feedback like that, and we'll get back to you as soon as possible. We're I'm now looking at putting more people to help me on these things because if we can grow this thing into something massive, I would love to. For the fact that we can collaborate and help more students. Um, but like I said, science is always fun, learning's always fun. So if you need any more of the books, notes, and other reference materials, they'll be located below or in the PDF linked out. So feel free to grab that. If you have any questions, again, please feel free to reach out. This is all about learning, gathering resources for you and what you're trying to do and your curiosities. As always, thank you for watching, and until next time, stay curious.